here. Okay, now we want to develop an expression for the concentration as a function of time and all positions. So in terms of our space, we have the positions X, Y, Z, of course, right? So the usual spatial dimensions apply. So X, Y, Z. By this X here, I mean the vector X. So sometimes we just call the position the vector X, and we understand that to mean the 3 dimensions. And so far, we have been dealing with the steady state case. So we've been able to say, well, at steady state, the molar flux, we can assume something about the molar flux, and we've been exploiting the fact that all the problems so far have been steady state. So we want to relax that now. We want to be able to develop expressions for the concentrations and the mole fractions, even if things are changing in time. So in this session, I'm not going to refer to any notes or anything like that. We are going to do everything from scratch now. And so we are going to use our understanding from the previous sessions. So we know we've understood our way through this basic expression, right? So we know about Fick's law. So Fick's law is the diffusivity against the gradient, so against the gradient dx dz, and then we have the contribution from the bulk. So if you just talk your way through this expression, you'll see there's nothing to remember here. This is the only way this could be. So we want to use this flux expression, and we want to we want to use it to get an expression for the variation of concentration across the space. Sorry, was there a question there?
Yes, sorry, I just wanted to ask, what question are we on?
Well, this will be towards the remaining questions in that tutorial set. So we talk about diffusion into a rectangular block and things like that, right? So for those remaining questions, which you couldn't do up to now, this is the theoretical development towards them. Okay, so this session is not exactly a tutorial, right? We use these sessions interchangeably between tutorials and theoretical development, right? Okay. So let's think about a problem. So let's sketch out a situation here. So let's say we have a slab, for example, a slab of concrete, right? And let's say our slab looks like this. So it's rectangular in cross section like this. And then we also have that the slab extends off into the distance like this. And, and so there's a large area out here. And what we are concerned about is the diffusion of water away from the slab, so out of the slab. Maybe we should actually add another layer down here. So we are concerned with diffusion, and that's because when we have a slab, whenever we pour concrete, concrete is of course a mixture of various silicates and water, and we want the concrete slab to dry. We want the water to leave the concrete slab, and that's part of hardening and so on. So we assume that on one side here we have an impermeable substrate. So the slab has been poured onto some surface that water doesn't penetrate into. So we We ignore diffusion in this direction, right? Looking down here, we assume that we don't have diffusion in this direction. We only have diffusion up into the outer air here. So we want to derive an expression that tells us how the concentration of water is changing over time. And we expect that what will happen is that initially we'll have a certain fixed concentration of water everywhere. And maybe let's make a small sketch for what we expect. So let's call this the Z direction. And so we have water diffusing in the Z direction, right? We assume that the concrete initial water concentration is much greater than the water in the air above that concrete slab. We know that there is a non-zero concentration of water in air, but that the concentration in this concrete here is much higher than that. So we anticipate that initially we have some concentration of water through the slab. So if we look in the Z direction, if we plot it like this in the Z direction, if this is concentration of water, excuse me. So if we assume this is the surface here, so let's label the surface to be L. So this is the position Z equals L. So we expect that up to L, we have some initial fixed concentration of water, and then above L, there'll be some other much lower concentration of water, much lower, but not zero. Now, what's going to happen the moment we expose the slab to air here is, of course, that some of the water will diffuse to out of the surface here. So that's maybe at T equals 1. And then because now you have a lower concentration here compared with there, then you'll get more diffusion penetrating and so on. So the concentration of water we expect is going to drop through the slab over time. And in fact, what's going to happen, I'm running out of colors here. What's going to happen eventually is that we'll get something like this, where your slab will have some concentration of water, which is much lower than the concentration in air. By the way, how long does it take to dry concrete? Does anyone know? Any takers? By the way, when I was in my early 20s, I did quite a lot of community work, which meant pushing concrete around for several weekends. Well, that's not how I know this, but yeah, Tashin, please go ahead.
So I think it takes about 2 days, 2-3 days.
2-3 days, yeah, that seems right, okay? And someone else says a day or two. It actually takes 99 years to dry concrete, right? That sounds crazy, 99 years. That's because when we look at a concrete slab, sorry, someone unmuted there, please go ahead.
I know, so I was just laughing. 99 years, not much.
Yeah. So that's because when we look at a slab, you know, we look at the top surface mainly, and then it looks pretty stable to us after a while. And that's because we are really looking here, right? This is what we can see. And in this layer, you can see over a short time, the concentration of water goes down very quickly. But you see, when you look deeper in, right, near Z equals 0, right? Z equals 0 is down here, and that's near the surface. So if you look deep into the concrete, it takes a much greater period of time, especially as the crystalline links form up here. It gets harder for the water molecules to diffuse through the spaces. So that's why it takes such a long time for concrete. Sometimes the building comes and goes before the concrete ever sets. And that's not a mark of shoddy workmanship. That's just the nature of diffusion. So now you can see here that there's nothing like steady state then. The concentration profile of water is always changing with time. And so what we want to do is use what we've learned to develop an expression that we can use to determine that concentration over time. Now, we've already defined the Z direction like so. So that's our Z direction there. Of course, we can also define an X direction and a Y direction. Right, so X, let's get this right. We should work with the right-hand rule, okay? So remember the right-hand rule. So if we should choose X in this direction. So we can look along the slab in this direction, or we could look into the page or into the screen. So that's the Y direction, and then the Z direction is up like that, right? So that would fit the right-hand rule. The comment here, can you upload the recorded lectures? So I have done that. Like I said earlier, here's our course. Here's the Moodle site. If you just click on this YouTube list link, you'll see all the lectures. Scroll right to the bottom. You'll find the last 4 lectures there, and I'll upload this. But like I say, yeah, we want to keep an eye on that attendance as well. So we've got X in this direction, Y in this direction, and Z like that. Now, we know in the Z direction, there is going to be mass transfer limitation, right? It's not a term we've used much so far, but mass transfer limitation refers to the fact that, that there is, like the name says, right? Exactly, there's a limitation to how fast this mass can transfer. So that's just because it's not so easy to diffuse through everything as we look up here. So there's a limitation to the rate of mass transfer up in this direction. And we can also imagine that there is, in principle, diffusion into the screen, if you like. So there's also diffusion in this direction. And then we can also think about diffusion in the X direction. So all of that does happen, but the gradients that result from that are negligible, because we don't expect that there are concentration gradients between points here and here. So we can define diffusion in this direction, but we don't expect it to be high in this direction, right? In the X direction, you've got the same concentration of water. So let's imagine we know the initial concentration of water in concrete. So let's just say it's 100 as a basis. So you'll have 100 in this direction and 100 in this direction. There's no difference here. The difference initially is between here and the air immediately above that. It's 100 down here, maybe it's 1 up there. So definitely there is a significant diffusion flux in this direction. But in this direction, at least initially, there's no difference. It's 100 here and it's 100 here. So there's no net diffusion flux in this direction. It's yeah, there's no net flux. And you see, as time goes on, that will be maintained. So as time goes on, the concentrations will change. So for example, at this position, maybe after 1 hour, maybe it's 80 here, then it will also be 80 there, because these 2 points are experiencing the same thing, right? Water is diffusing out in this direction. And so we are losing it in the same way on both sides. So if that's the case, then in the X direction, there's no difference. It's going to change from 100 to 80, but in the X direction, both these are 80. So this is still a net zero in this direction. And the same thing applies as we look into the screen. So looking into the screen in this direction, we initially had 100 here, and then we have 100 there. So there's no net difference. And then after some time, it's 80 and 80. Again, no net difference. So looking into the screen in the Z direction, there's no concentration difference. So we can safely say that we can ignore the X and Y directions in terms of concentration gradients. So that's true if we look at most of this concrete. You could also say, well, what about the fact that the slab is a finite thing, right? For example, there might be another wall here. So the slab might be up against some wall here. And then you can say, well, then right next to that, next to the wall, there might be a different concentration to what's inside the concrete. So that's what we call end effects. So near the ends, we expect there will be some differences there. But if this distance is great enough, right? If this distance is great enough, then we can say the end effects are small. So we'll ignore end effects, and the development we are going to do refers more to the interior of our slab away from the ends. And so for most of this concrete, the equation we develop is going to apply. Any questions or comments on that? Okay, so I was actually getting into the habit of saving before I delete all these things. So let's say 22. Okay. So let's redraw this, and let's see. We'll say we've confined ourselves to the Z direction. We've said now we are not so worried about X and Y, only at the ends, only as end effects are those, is there any difference in concentration? So we are only concerned with the Z direction, and we are defining Z like this. And for all these types of problems, this is the type of thing you want to do. You want to start with a little sketch that outlines everything going on, then figure out which dimensions matter, and then you settle on these are the dimensions that I need to cover. So we've worked out only Z matters. And what we do next is define a control volume. So we've got our real system. This is our concrete slab, this green block. And for us to develop our equations, what we will do now is define a small region in that block. So we pick a position, we pick a sub-volume. And we want to pick a sub-volume because we want a small enough region where we can assume that there are, that certain assumptions will apply. And we'll explain what those are now. So let's just say we are picking a small space like this, and we are defining this to be at Z and Z plus delta Z, okay? I need to write a little illustration maker. So we've got here, this is position Z, and this is Z plus delta Z. And so on this picture, we know that we will get diffusion. We know that the concentration gradient, that there is a gradient out here. There's a low concentration and a high concentration. So we know overall our diffusion is like this. We also don't have velocity, right? Water is not flowing through here. It's just diffusing only. And then we will have water diffusing in at this specific location at Z. And water will also diffuse in at Z plus delta Z. So based on that, let's draw a picture. One other thing to mention is the area in this direction. Let's draw it. So we can think about the top surface here, right? This is a slab which looks like this. So in this direction, so here on the top surface, there is a cross-sectional area. Which we will just define as AC. So the area here is AC. And so when we are diffusing in this direction, you can imagine a big plane over here, right? I'm not going to draw the whole plane, but you can imagine, oops, you can imagine here, there is this whole plane. There is this plane that's going in here. And yeah, the plane goes all the way around to there. Down to, it's about here. And then the same applies for the lower layer. So I'll just draw it for the one layer at Z plus delta Z. You can draw the same plane for Z. So that whole plane, we are assuming it's a regular block. So the cross-sectional area AC, the top area, is the same as the area of this plane. And so the diffusion we are talking about at Z and at Z plus delta Z, that's into this whole plane, which has area AC. Okay, and we'll need that just now. So let's copy this. I think it's best to do it this way. So there's our sketch. And so it's very important when you start this development to produce your sketch in such a way that it's clear what your control volume is. So our control volume is the space between Z and Z plus delta Z with a cross-sectional or a surface area of AC. So in the X and Y directions, maybe let's write that like that. So in the X and Y directions, area is AC, which will be the area into which the water is using at each layer. Z. So is in the Z direction. Fusion in X and Y are much lower in Z since same concentration expected except at end points. And those we said are called end effects, right? Okay, so that just describes the problem. And you know, the rest, I know it seems quite mathematical, as we'll see, we get these giant expressions eventually, but it all starts from here. If the understanding at this level is not absolutely correct, if you haven't defined everything rigorously, then the following developments, you'll likely have many errors in there. Okay, any questions about the physical setup so far? So,
So is it okay if you could just go up for bits? I just wanted to see those first two equations which you wrote down, or assumptions.
yeah.
Okay, yes.
So yeah, this is just pointing out there are 3 dimensions we always have to think about, and then there's time. And so this is, if you like, the independent variables, T, X, Y, Z. That's in rectangular coordinates. We'll see we can also do this in spherical coordinates, in cylindrical coordinates. So yeah, that's just defining the space. Okay. Okay, now what we want to do is write a balance over this control volume. So we've defined the small volume between Z and Z plus delta Z. So we can say the volume of the space, delta V, is equal to, we know it has that area, and we know the distance between Z plus delta Z and Z is delta Z. So that's the volume of our space, right? We can also define CA, and CA is, so that's the concentration of water, right? A is water. So that's the concentration of water as it varies both in the Z direction and in T. So like we said earlier, I'll close that drawing. Like we said, it is changing. Let's see, where's the folder? So we said, yeah, I need to save this. So we said that we do have the concentration gradient, the concentration as it varies in Z is changing in T. So, so that's why here now we are defining that there exists a concentration. It changes in T and it changes in Z. We are not worried about changes in X. So we can define a concentration which depends on those two variables. And what we can say then is that the number of moles of A, so we can write that as NA. So lowercase n is the number of moles, right? Uppercase N is molar flux, right? So lowercase na, number of moles, is of course equal to Ca at T and Z, and that if we multiply that by the volume, delta V, then we should call this a delta Na also. So that is an estimate of the number of moles in our control volume. So the number of moles in this control volume can be estimated or approximated as the concentration at this position multiplied with the volume of that whole space, which we've just established is that. This is an approximation, right? So we should strictly write it like this. Another approximation could also be that instead of at Z, we could do this at Z plus delta Z, right? So in this case, we would be looking at the top edge and saying, what's the concentration there? And then multiply it by that volume. So, so those are both approximations. And of course, a better approximation would be the average of the two. So 1/2 times the average of these two concentrations. But even in this case, it's also an approximation because the concentration gradient of A in the Z direction is not guaranteed to be linear, right? Only if this is linear will this average give us the exact concentration, the exact average concentration, but it's not guaranteed to be so. So this is a better approximation, but it's still an approximation. These are worse approximations. And of course, it's going to get better as we take smaller deltas. So as we let delta Z go to 0, this space becomes smaller and smaller, and so the approximation gets better and better. So these are all approximations. So we might as well take the first one. It's not the best approximation, but we know it's going to get better as we take a smaller space. So that's going to be a good enough approximation for us for now. So we can say that there is a rate of change of delta Na. So we can say d dt. So the rate of change of the number of moles in the space, which is delta Na, that's going to equal, and so the rate of change of the number of moles in the space, right? So now we are talking about inside the space here, right? This finite volume, delta V. We can see there are only two things happening. A is arriving by diffusion here, and then it's also leaving by diffusion here. When I say leaving, I should have actually drawn this squiggly line just on the starting on this upper edge and pointing up like that, right? So we can write this then as the molar flux of A. So molar flux of A, and we want to specify the spatial position Z, and then we want to multiply that by the area that's presented to diffusion. And this is another source of extreme error. So whenever you are trying to approximate the molar rate in a particular direction, always remember, then you'll take the diffusion rate in that direction, and the diffusion is into the area that's normal to that. So in the Z direction, there is, so in the Z direction, the area that's normal to that is AC, right? X and Y are normal to Z. They are orthogonal, or they are at right angles to Z. Any position on that surface is at right angles, or any vector you draw on that surface could be in any direction. As long as it's on that surface, any vector you draw there will be perpendicular to the Z direction. So we say that as it's normal to that direction, or orthogonal. So so that's the flux in the Z direction. So the right area to multiply by is AC. And you see, in these problems, there will be many, many different areas to deal with. You could also talk about the area of this end over here. And then there's another area where this green box is drawn. So there are different areas that you can define. So you have to be very careful. If you are looking in the Z direction, then the area that's normal to that is in the X and Y direction, and that is the area AC. Okay, so that's what's coming in. And then what's coming out here is going to be minus NA, and this is going to be at delta Z times AC. And really, that's it. That's everything that's happening in our system. This equation fully describes what's happening in this sub-volume. But it's written in a form where the variables are not on the same, it's not so easy to work with this equation because the variables are not on the same basis. So let's start converting them. First off, this delta NA we established up here is equal to this. So we can replace this with, delta NA with this. And then this delta V we said up here is equal to this. So that delta V we can replace like so. And then this NAZ is something we need to unpack. So let's go back to our general expression, and let's see in this context, how would we write this? So our NA as a function of Z, NEZ, looks like this. And let's just remind ourselves here that this gradient is a Z value as well. So this is sub Z. So this is the gradient at position Z. These are also at position Z. Okay, and in this case, B is the concrete, and we know that concrete is not moving around. So we can say B is the concrete. And well, we can think of two ways to view it. One is we could say, well, at this stage, B is also liquid. It's still hardening, so it can be in equimolar counter diffusion to A, but that's not the majority of what's going to happen, right? Initially, that may be true, but as the concrete sets, the majority of the challenge to mass transfer, to transfer in this direction, is going to be due to A having to diffuse around the B that's set. So let's say NB is overall not moving. So it's the concrete, it's not really going anywhere, so that's the case. So our NAZ looks like this. And so, so we can take that off there. So it's XANAZ. And then we can also, well, we can take it across to that side, and we can rewrite this as, we can do the usual thing here, NAZ into 1 plus, or rather 1 minus XA. So that's our expression. Or we could say this is equal to NA, because we actually need this expression NA, and we want to divide it here. Let's do it like this. Right, so that's NA as a function of Z. We do want to point out here that this XA is a function of Z as well. Right, so mole fraction is changing in Z if concentration is changing. The other thing we can do, okay, let's leave it like this. Let's work like this. So that's our NA. So let's go back to the expression we were developing, which is this one. Just copying it there. So it looks like we have to work in terms of XA. So let's remove the total concentration. Sorry, what was that?
Sorry, sir, could you just go up a little bit? I think I might have missed something.
Yeah.
Oh, okay. Okay. I see now. Never mind. It's okay.
Okay. So if we remove a concentration here, right, we can say the concentration is equal to the total concentration times the mole fraction, right? So we can say concentration, which we know is not the total concentration in this liquid is not changing. So we can rewrite it like this. Okay. So that's one thing we can do to update our equation. And then the other thing we can do is, so we can see AC occurs throughout this equation. So we can cancel that everywhere. So the AC can cancel. And then we can substitute for this NAZ. So let's just do that a bit separately. So for NAZ, we can replace by this form. And this is Na at Z. So this form is fine. For this one, we are going to do it at Z plus delta Z. So here we need to say 1 minus xa at z plus delta z, and this is z plus delta z, okay? And we've got a minus here, we've got minus here, so this is a plus. Okay, now what we could do, and this is going to seem a little strange and unnecessary, but bear with me. What we could do is say that this is a certain function that's given at a certain z position. So what I want to do is just extract that there. I actually want to put all of this inside this square bracket. Okay, this is, we need to do it again. So we can say all of this, we'll put this inside brackets and say this is all at position Z, which looks pretty obvious. So we can say this is at Z equals Z, right? And then we're going to do the same thing here. Let's sort this out. And now we're going to say here, this is at position Z equals Z plus delta Z. And so that means this A, or this term, we can just write this as a Z, because the fact that this Z is at Z plus delta Z, where this Z refers to the current position Z, which is that. So now if you look at this, you can see you've got the same function in both these terms. And both these terms are evaluated at different positions, at different Z positions, but they look like the same function, okay? And what we would do next is divide through on both sides by delta Z. So we're going to write this as that divided by delta Z. Right, so we've divided by delta Z here. And if you look at this equation here, we can see it's a function at Z, right? Maybe a better way to write it is to shift that term. So all I'm doing is moving this term to the other side here. So it's the exact same thing. I'm just writing it on that side to make it obvious that this is very much a derivative. Remember, when we say dy dx is equal to, and then we'll say that's equal to y at x plus delta x minus y at x divided by delta x, right? And we'll say here limit delta x going to 0. Right, so we know the from basic calculus, the definition of the derivative is this ratio as delta x goes to 0, right? So that's a straightforward definition of the derivative. And so if we do the same thing here, we can say, let's take the limit. This is for delta Z going to 0. So if we look at this, this is the exact same form as we have down here. And so this is nothing but the derivative ddz of this function. ddz of that. So that's our expression. And you see this equation is a kind of a friendly form now, because it is a PDE, but you can see it's a PDE in XA. So now we have a nice equation which we can just go ahead and integrate. We do, by the way, we could concentrate, cancel the concentrations as well. They are on both sides, and they are not changing in Z. The diffusivity also is a constant in Z. So we can write it like this. And that's it. That's our equation. And that's what we're looking for now. We want an expression that can be used to evaluate how the concentration is changing in T and Z. What we actually have here is XA. We can see that if we integrate this, this is going to give us the mole fraction of X in T, right? When we integrate it, we are going to get a T dependence. And then we also have a Z dependence here. So T and Z. And then, of course, we can say that the concentration Ca as a function of T and Z is going to be the total concentration C times XA at T and Z. Okay. So that's what we are looking for. And I must say this section does get a bit, when you take a step back and you look at all of this and you think, oh, look at these nightmare equations. But when you get into it, when you read each line and look at we are doing it in short steps each time, you can follow all this. And by the way, when I'm doing this, I'm not looking at any book or anything like that, right? I'm deriving this directly without using any memory. I mean, the most memory I've used here is this, and even this you can talk your way through. So all of this, there isn't a single step here that involves some other outside information or something that you don't already know. So you can definitely do this, and as you are doing it, it looks kind of scary, but just keep at it, and you'll see you'll get the expression there. Okay, any questions or comments on that? Now, when you see an equation like this, so in your maths courses, you've done PDEs so far, is that right? Partial differential equations, it's second year, second semester. Have you seen PDEs in your first semester?
No, sir.
Okay, so a PDE is a partial differential equation. So these should actually be written as partials. So these derivatives, if we want to specify that this must be explicitly in this direction, partial. But anyway, that doesn't, don't worry about that right now. Let's just leave these as Ds, okay? So a partial differential equation is one in which you have more than one derivative, right? That's the simplest way to view it. There's more to it than that, but that's one standard way of looking at it. There's more than one derivative in your equation. So earlier we started with simple, right, with a single derivative that was just in T, but there was a hidden derivative in Z. So because our space is between 2 points, and because there is there's diffusion, well, even without the diffusion, as long as you've got a difference between 2 points, there's inherently a derivative. There's a gradient somewhere in our system. So we are familiar with ODEs, right? Maybe just to check that also, you've covered ordinary differential equations in the first part of maths, right? You're familiar with equations, maybe even to say it like this, like dy dx is some function in x and y possibly, right? Of course, that's first year maths, right? You know this. So we call these ordinary differential equations. And then if you have more than one variable, right? A simplified way to think of it is if you have more than one variable, then you have a partial differential equation. So it's just the case that now on the right-hand side, you can have more derivatives, okay? So any questions or comments on that? Now, to solve these equations, of course, for example, in this case, we typically had some boundary condition or initial condition. So we had something like this. We would say that we happen to know at one specific point what the value was. So if we pick some point where x equals x0, then we happen to know that it was y0. So for example, let's take a step back and just do a simple example. Let's take a vessel like this, and we are feeding in here and withdrawing here. And so there's a certain volume here, and then there's a volumetric flow in here. So we'll call that Q in, and there's a volumetric flow out here, Q out. So if we were to write the differential equation on this, we would say simply the rate of change of the volume here. So let's imagine there's a certain level in this tank. So there's a certain volume that's in this vessel, certain volume here. So we would say simply dV dt is Q in minus Q out. Minus Q out. So let's just copy this. Yeah, let's kind of do this as a problem 0. So we have the simple rate of change of volume in here, and then we would say, well, we want to integrate this equation. I don't know why I didn't just do it here. dV dt equals Q in minus Q out. Right, so that's our governing equation. Now, this is an expression of the change in our system, right? It's telling us how things are changing. In its form as it is, it's not going to tell us what the volume is currently. Without integrating this, we won't get V of t, right? This is actually what we want to know. We want to know how is the volume changing with time in this vessel. And let's take a simple case where maybe Q in equals, let's say 5, and that's of course meters cubed per second. And let's say Q out, let's just say that's 2 cubic meters per second. Right. So if you look at this, then clearly dV dt is just 5 minus 2, which is 3. So this is 3 cubic meters per second, okay? And you could integrate this. So you can say V, right, dv dt is constant. So V is simply 3 times T. But you see, whenever you do integration, it's between 2 points, an upper limit and a lower limit. So your lower limit is V naught, so minus V, or let's define that to be V naught, your lower limit, let that be V naught. And equivalently, this will be T naught. So
excuse me, sir.
Yeah.
Sir, I'm really sorry. I'm really struggling to understand how we got to this point, because before, sir, we were looking at molar flux, we were looking at concentration. Now we've come to volume. I'm just really having a hard time grasping how we went from.
So what I'm
from
trying to
what we
do
were doing
here
before
is
to
explain what these, see these derivatives, and if you just look at the equation like this, it's hard to understand what all these gradients mean and how we are ever going to get to a solution here. So what I'm doing is just taking a step back and giving another sub-example. And what I want to talk about are, the limits of integration. So just take this as another example just now, and we'll see how it relates to the example we were doing over there. Okay. Okay, so if we integrate it, this is strictly speaking the form that we need. And so what we can say here is that there was some initial volume, and this was the volume when T was equal to T naught, right? So there we can say at the time T naught, the volume was V naught, right? So this is a condition. This is additional information. We do have this very general form. So this is always true, right? If we pick any instant in time, the volume is changing in this way. But when we write the equation like this, if we solve this equation, we'll get a form with some extra constants in them. So we need additional information. And so the additional information comes in the form of, in this case, what's called an initial condition. It's saying initially at T equals T naught, the volume was V naught. So for example, let's say in this case that our initial volume was 10 cubic meters. 10 cubic meters. So then we can say our solution to this equation, V of T is going to be this plus V naught. Our volume as a function of time is equal to V naught is 10 plus this. So this is now a solution in a form where we can actually get the volume. So we can say if my time, so let's also say T naught equals 0. Right, so the initial time T naught is a 0, and so we can get rid of this. So this is 3T plus 10. So if the time is now 10 units after the initial one, then this is 30 plus 10, and it's 40. So this equation is useful now. Now we can use it to calculate the volume at any time after T naught, right? And you see, we got that through an initial condition. So I'm just explaining all this because maybe the ODEs are kind of new. And now that we are meeting PDEs, I just want to make sure that all this is clear. So are there any questions on this? Is this quite clear what we are talking about?
So I just want to know that 10 is it an example, or you got it by doing something?
Yeah, this is extra information. So this is in the context of some problem. We'll have to be told with this question. So let's say in the question we were told, a vessel initially holds to 10 cubic meters is fed by a stream at 5 cubic meters per second. From which a stream at 2 cubic meters per second leaves. What is the volume as a function of time? So this has to be given to us as additional information.
Oh, it's a given value. I get it now.
Right. Yeah, because so you've got your general equation. So that's how you start. You get the general expression describing the whole system for any instant in time. Then you make it a bit more particular. You can stick in the general values. So these apply for all time as well. So it doesn't say there's a change in those flow rates. So that applies. And then you can get a general expression for the rate of change of the volume. And then you use the conditions around that. So we are given a so-called initial condition. So you can use that then to get an equation finally that can actually give you numbers. So at this stage, you have something that looks like a solved equation, but you can't actually get numbers out of this, right? The V naught is an unknown thing. But because it's given to us in the problem, then you can actually get numbers. So the reason I'm pointing all this out is that here, when we look at this equation, there's going to be an initial condition that we need. We can see we've got a DDT here, and we will need extra information. We will need to know something about, for example, initially, what was happening in the system. And we also have other gradients. We've got a DDZ here and then another DDZ over there. So for each derivative that occurs in our expression, we need another piece of information. Those are so-called boundary and initial conditions, right? They are the same thing in principle, right? It's additional information. It helps you nail down a solution. Because you could view this as a kind of floaty thing. You can say, well, my solution, it's going to do something in time, right? My volume in time, it's doing something in time. And then you say, well, Q in and Q out are fixed. So if Q in and Q out are fixed, then dVdt becomes fixed. And then you say, well, now it's not so floaty. It's some line with a gradient. It's a gradient like that, or it's a gradient like that. Depends whether Q in and Q out, which one is bigger. And then you say, well, there are specific numbers for Q in and Q out. So then you say, okay, then that makes it then it's this specific equation. And then you say, but I don't know where this line is sitting. Is it sitting here or is it sitting there? Then you say, well, V naught is fixed. It's fixed at this value. Then you say, okay, then that's my solution. That's exactly how V is changing with T. So that is an important way to think of differential equations, right? Like the name tells you, right? So not ODEs, not PDEs, just generally differential equations, all differential equations. They are equations of change. They tell you how things are related to each other in terms of their changes. How is the mole fraction related to the diffusivity through the position and through the time? So how are the changes in time related to the changes in space? So that's a differential equation, a relationship of changes. So if you only have an equation of changes, it's not going to give you a specific solution. So for example, if I tell you, you are sitting in a classroom and overall there's one person coming in to that classroom per second, right? So that's useful information. I know one person, right? Maybe there are 20 people coming in and 19 people going out per second. So on balance, there's one person per second coming in. So that's a statement of changes. You cannot use that to work out what your total number of people are in that classroom. So there might be 500 people in the classroom, or there might be 2 people in the classroom. You don't know, because you only have an expression of the changes. But if we can get the conditions around that, if we can get the value at a particular instant in time or at some point in space, then we can start to get a particular form of this. And that can help us get to the actual mole fractions as they change in time and space. Okay, any questions or comments on that?
Sir, could you go down, please? More.
There's nothing below that.
Could you go up, please?
Okay, maybe ask your question. What is the question you have?
No, so I just want to take down that question yours about that volume.
Okay,
volume.
so just remember the whole class is, all of these I am saving to Dropbox. So, you know, in terms of your writing the thing down, rather get it from there. Okay, so if you have a question about the content, right, go ahead and ask that. Okay. Okay, so that's that is how we relate, how we get to specific solutions. So from our general law, from our understanding of the physical situation, we get a relationship among the differences in the system. And then from additional specific information, we get to a particular solution. Okay. So we'll deal with boundary conditions in more detail in a future session. So for now, let's just focus on getting these statements of change, right? That's how you view this. It's an expression of change. It tells you how time and space and the variable of interest are related among each other. Okay, let's take another example now. So let's think of a new situation. And I want to work with different coordinates this time. So let's say, let's think about that particle type problem. So we had a particle and, and we had component A being consumed on the surface of that particle. So we said A was diffusing towards the particle because it was being consumed on the surface, and component B was diffusing away because there was no B in the bulk fluid. And because we were producing B on the surface, then we had a high concentration there. So the diffusion was in that direction. So we have this problem, and we would like to know how the concentration of A changes over the space. So let's just restate the problem here. So question 2, if you like, given the consumption of A on a particle such that we have A giving us 3B, develop an expression CA as a function of T and R. Right, so now we want to know how the concentration is varying as a function of T and R, and it's not steady state anymore. Not steady. We'll say here the surface reaction rate is high. And by that we mean in comparison with the diffusion rate. I guess that's enough for us to start with. Okay, so we can see now we are not steady anymore. So when we did this problem before, we were at steady state and we could make certain approximations about NA. So we could say NA, so maybe let's just list it. When steady, we can say NA, and this was at some R position times R squared equals NA at R naught times R naught squared. So if you go back and look at it, you'll see we could, when the profile was steady, when concentration wasn't changing with time, we could say this, right? But now it's not steady anymore. We can't use this now. Okay, so what we want to do then is take the approach we described a bit earlier. So we want to know how A is changing in the fluid. So that's past the particle surface, okay? So what we will do is again choose a control volume. So let's pick a point here. And let's pick another one, say here. And so these are two radial positions. And I just want to make clear that these are just construction lines. So there isn't some kind of shell or anything. We are just picking two arbitrary positions in space. And the inner space is at R, and the outer one we'll define to be at R plus delta R. So we can say this one is at R, and this is at R plus delta R. Okay, and so this defines our control space, right? So the region between these two imaginary spheres, that's what we are talking about. So towards answering this question, we always have to find a sub-volume. And this time we've chosen it to be spherical because that's how the diffusion is happening. Right? In the earlier case, we had a rectangular slab, so rectangular coordinates made better sense. In this case, the diffusion is in the R direction, and it's in all R directions, right? You could pick any pair of angles. Remember, in your spherical coordinates, if you pick a theta pointing out of the screen, so there's a theta 1 here, and then there's a certain other angle. So that's theta 1, and then you can pick like a height above. So in this direction, there's a theta 2. So theta 2 there. So those two angles. So for any pair of angles, theta 1, theta 2, we have to think about a certain R position. So R is fixed in spherical coordinates. So it's basically a sphere. So at R, we have one sphere. At R plus delta R, we have another sphere. And think about a ball, right? So a real ball in the real world, it has a certain real thickness, right? So maybe your ball has a radius of half a foot. Say the ball has a radius of let's say 20 centimeters, and maybe it has a thickness of 5 millimeters. So the skin of the ball, the 5 millimeter skin of the ball, that's what we are talking about here. And so that has a certain volume, right? 5 millimeters, and then times the area of the ball, that will be, there's a certain volume inside that ball. And so what we are trying to do is figure out what's the number of moles in this thickness of the ball, right? It sounds weird, right? the thickness of the ball, but that's what that's how we are defining our control space. So let's just copy this little sketch. Where's my snipping? So we're copying this figure. And so that's the first thing we do in answering any of these questions, right? So that's our geometry. And then we can say we are interested in the number of moles of component A between R and R plus delta R. So we can define that to be delta in A, and that's equal to the concentration of A, and we'll call that the concentration of A at position R, and then times the volume delta V. So if we pick the inside concentration here at R, Ca at R, and then if we multiply by the volume of our subspace. So our subspace is the thickness of the ball. So delta R,
Excuse me.
sorry, delta V. Okay, 1 second. So delta V is going to be the area of the ball. So 4 pi R squared. So, right, so that's the inside area. So at position R, that's the area of a sphere, right? So the area of the sphere times the thickness of the sphere, which is delta R, right? So that's your delta V. This is, of course, an approximation again. So this is only an approximation. You can get the exact volume instead. So you could say the exact volume, right? Exact volume is actually, you can get that by taking 4/3 pi, 4/3 pi times R plus delta R cubed, right? That's the formula for the volume of a sphere, 4/4 pi R cubed, right? So that's the volume of the outside sphere minus the volume of the inside sphere, 4/3 pi R cubed. So this is the exact volume, but we are going to use this because we get some nice cancellations, and we know if we take delta R small enough, this approximation gets better and better. So yeah, that's exact, but we are going to settle for this approximation. And also this approximation. Remember, also CA, that's taken from the inside surface, not, we don't know, well, it's only an approximation. It's not the exact mean concentration across that radial position. Sorry, there was a question there.
Yes, at the top when you were stating when steady, NAR is times by R squared is equal to NAR naught times by R naught squared. You said can use this now. Isn't it we can't use this now?
Yeah, sorry.
I know it's not that you.
No, thanks for that. That was an error. Yeah, I should have said can't use this now. That's what I meant. Let's emphasize that. Cannot use this now. Yeah, thanks. Okay. So any questions or comments on this so far? Okay, so now we have an estimate for the change of the moles inside our subspace. And now let's look at the rate of change of that. So as before, we said ddt of delta NA. So the rate of change of the moles in this thickness. And by the way, again, this thickness, it's not a real thickness. There's no actual ball there. This is an imaginary space, right? We are arbitrarily picking in the fluid some position r from the center and some other position r plus delta r. So that's some imaginary ball and an imaginary thickness. So inside that region in the fluid, we have a certain number of moles, and that's changing because we have component A diffusing just on the inside here. So that's going to be NA, and this is the flux at position R. And then the area on the inside there is going to be 4 pi r squared. And then leaving the space is going to be out here. We've got the molar flux at position R plus delta R. And the area there is 4 pi r, and we need to say here r plus delta r squared. And again, notice that we are talking about the area that's normal to the flux direction. So we are fluxing radially. So the area that's normal to the radial flux is the surface area of that sphere. So that's the surface area of the sphere. Of course, you could also define the cross-sectional area across the sphere. So the area of the circle is pi r squared, but that's not appropriate, right? Pi r squared, the area of the circle, we are not diffusing in that direction, right? We are diffusing outwards against the whole sphere here. So that's the area that matters to us. So we have this expression. We can substitute for delta NA. So we can rewrite this as CA delta V. And then delta V, we are approximating with this. And you can see these are selected radial positions, R and R plus delta R. So they are not going to change with time. So we can take this out as a constant in time. So we can write this here as 4 pi r squared delta R. So that's what we can write on the left-hand side. On the right-hand side, it's still a bit unfriendly because we don't know how to deal with these NAs. So let's go back to our original expression. So we know this always applies, right? This is generally true. So this is what we can say for NA. In this problem, as we established before, NA equals, and it's 3 NAs equals minus NB, right? So we talked about this in detail. They are fluxing in opposite directions, and what is it? What do we have? 3 NAs. So 3 Bs come out for every one of A coming in. So NB is 3 times NA. So we can substitute this as show why it's leaving a big space like this here. Anyway, so NB is minus 3 NA. Minus 3 NA. So overall, this is going to be minus 2 NA. So that's there. And then we can just take that across to the other side and write this as NA1 plus 2XA. Okay, and that's our equation. So we can rewrite this, of course. We can divide out that extra form. And by the way, it's we are dealing with radial positions this time. So that's R. That's R. So this is at position R. 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 Oh. A bit tedious to make a mistake. So this is changing in R. So NA as a function of R, we're going to divide here. Right, so that's the expression, and we could emphasize that XA is a function of R, right? So that's what we have. So going back to the balance we were doing, let's stick that in here. And let's substitute for NA. So NA of R looks like that. Oops. And then NA at R plus delta R is that. And now we just have to specify plus delta R here. So this is all at R plus delta R. Okay, yeah, the equation is looking quite nice, right? Let's try and make things a bit, let's try and cancel what we can. So the 4 pi's can all go. And you know, before we could cancel areas, right? In the earlier example, AC canceled nicely everywhere. But in this case, you can't cancel areas. So you see the area term was the 4 pi r squared. We could cancel the 4 pi. This r squared can cancel with this r squared. But then here you've got this r plus delta r squared. So we can't cancel r squared in this case. This we can say is a plus. And what we want to do as before is write all of this as a function of r. So we're going to say here, let's just copy this part out to here. Then we'll stick all this in here. So we are emphasizing all of this is happening at the R position. And then again here. And by the way, I should put this in as well. Okay. And then here, I'm going to stick this in to the brackets. Yeah. And now we are saying this is at R equals R plus delta R. So I don't need to say this here. I can write this as an R now. And also this R plus delta R squared, if I move that into these brackets, where I've specified what R location we are at, then instead of writing it like this, I can write this as R squared, where it's understood this R equals R plus delta R. And I'm not trying to cheat or something here. I'm not going to say now you can cancel these R squareds. It's wrong to do that, right? You can't cancel these R squareds because if you like this, all of this is a function of R plus delta R. So this is still R plus delta R squared. You can't cancel this with this R squared and this R squared. So you have to leave it there. The CDAB, I guess we can remove as constants, but let's just leave them there for now. And then this plus, let's just move this to the other side. So it looks like this, okay. And now what we can do is divide by the delta R. So dividing by delta R on both sides. Right, and then we can take the limit as delta R goes to 0. So lum delta R goes to 0. Then we shift all this in. And we can see here, we've got the exact same function in both positions. CDAB over 1, 2x dx dr, CDAB over 1 plus 2x dx dr, and then r squared as well. So if you look at this, it's just, this is like f at x plus delta x and f at x, and then we are taking the limit. So this is nothing but a big old derivative. So we can say all this is equal to ddr of this thing. This ddr, so ddr of that. And that's basically it. That's our differential equation. And this time it's in spherical coordinates. And so this describes for us, this is another partial differential equation. You can see the variables here are time t and radial position r. You've got 2 derivatives in r and 1 derivative in t. Okay. And so far, that's the expression. We know we will need boundary conditions. We'll need additional information to solve this equation. But for now, we are happy that we at least can derive an equation for this form. Okay, any questions or comments there? In terms of how do you access Dropbox files, just click on that link. It will open up, it will take you to a web page where all the files are there, and you can just click them. Or you can go on Moodle. So I did show earlier, you can just go here on Moodle and here under repo files, if you click that, you can just open the files there. But I do recommend you really start working with Dropbox because, yeah, maybe I'll put the link in the Dropbox link, but check in the announcements. I did post the Dropbox link. So you just go to that link. I do recommend you install the Dropbox client on your PC. There's Dropbox. People also use, what is that other, that Google one, Google Drive, and then Microsoft has another one. So there's lots of these cloud storage options. Do work in them so that your work gets saved always and you don't lose like your final design or something like that. Okay, in terms of this content, any questions or comments there? All right, so in the tutorial, you've got other problems of this type. So largely it's about interpreting the physical situation. And then it's a simple matter. You must regard all of this as the simple part, right? This part is easy. After you've done it enough times, you'll see, okay, I just need my control volume. I can write a little balance. I can work out what my flux expression is, substitute it, convert the derivative form, and I'll get my expression. So all this is kind of mechanical, right? This part is easy. The hard part is this, right? Interpreting your situation, knowing what can be applied, what can't be applied. So converting that text description into this. I would say if you take enough time to do this part, the rest just falls into place, right? So you've got some interesting problems in that tutorial. I've got some additional other interesting problems that we can look through. So work through that. Be sure that you can derive these statements of difference relationships, right? The differences in the R direction, differences in the time direction. So how do you relate all of those things, right? And you couldn't have just sat down and said, oh, the concentration is related to the change in the radial position in this way, right? It's not obvious that this is true. But when you work through it, when you use the actual balances, then you get the exact form that's rigorously true. So that's what we are trying to establish here. So do be able to do this well, right? And then in the next theoretical development, we'll look at what boundary conditions we could start applying here. All right, any questions or comments there?
Yes, I just want to confirm something.
Mm-hmm.
Can we go to that sphere kind of shape? I don't know if it's a ball or sphere. I just want to ask something.
This one? Yeah.
Okay, we have two radius coming from that small circle, right?
Yeah, these are two radial
lines.
positions.
The first one is r, right?
Yeah. This one.
And the second one is r plus, yes. Then the second one is r plus delta r, right?
Yeah.
So I just want to confirm that the reason you're saying the second one is r plus delta r is because you're adding the thickness of that, I don't know, that one you call delta r.
Yeah.
Is it? Are you just adding it on that r to call it r plus delta r?
That's right. So we are saying there's the inside face. So this volume that we are interested in has an inside face at r and an outside face at delta r. So if this was a real ball, and if the ball had a radius of say 20 centimeters and a thickness of 5 millimeters, then this position here on the outer surface, this would be 20 centimeters plus 5 millimeters. So yeah, if you define the ball radius like that, if you define the ball radius in terms of the inside position, so if the inside position is 20 centimeters, if r is 20 centimeters, and if there's an additional thickness of 5 millimeters, then this r plus delta r is 20 centimeters plus 5 millimeters. And that was our choice. We chose those two positions, right? Because there isn't a real ball here. We are just choosing two positions because we want enough of a difference that it's going to start showing us how our molds are transferring. Does that answer it there, Freedom?
Yes, very clear, sir.
Thanks. Okay, any other questions or comments there? All right, if not, that's it for today. See you in the next one. Thanks for coming.